Hi, friends, and welcome to the latest episode of the Gradient Podcast. If you've heard enough of these episodes, you might be able to sing along at this point. We interview various people who research, build, use, or think about AI, including academics, engineers, artists, entrepreneurs, and more. I'm your host, Daniel Bashir, and in this episode, I am very excited to be interviewing Hattie Zhou. Hattie is a PhD student at the University of Montreal and Mila. Her research focuses on understanding how and why neural networks work, based on the belief that the performance of modern neural networks exceeds our understanding, and that building more capable and trustworthy models requires bridging this gap. Prior to Mila, she spent time as a data scientist at Uber and did research with Uber AI Labs. This was another long and very fun conversation. If you like empirical theory, I think this is really a great episode for you. Hattie's work is just phenomenal and very interesting. She's an incredibly thoughtful person, and I really can't wait to see what's next in her research journey. We have a number of really exciting guests coming up this year, so as always, if you aren't already subscribed to The Gradient, go ahead and follow us wherever you're listening to this podcast. You can also follow us on Substack, where you'll get notifications whenever we release a new podcast episode, article, or newsletter. And now, without further ado, Hattie Zhou. Hattie, as always, our first question is a little bit about the origin story. So I know that you kind of started doing AI research as a side thing, and I'd love to know what got you interested in doing that in the first place.
Yeah, so I'll start a bit earlier when I first got interested in machine learning because my undergrad was actually in business. I did my undergrad in finance mostly, and never thought that I would do anything sort of related to machine learning or anything technical. But near the end of my undergrad, I was taking a class called value investing, where they teach you how to value stocks. And basically, they give you this template that you're supposed to fill in the inputs and output kind of the value of the stock. And I really wanted to automate this process because I'm lazy, but I realized, a lot of these inputs that you need, you can pull from financial statements and things like that, but some of them are more discretionary. So things like, how risky is the business model? How good is the management team and things like that. So, thinking about how one might be able to automate things like this that can't be encoded into rules led me to discover machine learning, and I was just really excited by the possibilities that you can do with the skill set. So I kind of then decided to go down this path and learning about machine learning, and had a few different jobs that were more and more technical. And eventually I was working as a data scientist at Uber. And at the time, Uber had a team called AI Labs that worked on fundamental research. And I saw a talk by Jason Yusinski and Jeff Clue, a talk they gave on AI neuroscience to the Uber audience. And they showed this, the performance of this neural network on classifying images, but also looking inside the neural network and seeing what individual neurons are actually doing. And that just was like the coolest thing I've ever seen. And it was really interesting to me that we had this model that was so impressive, but it seems like as a field, we didn't really understand how it works and why it even works. So that got me interested in doing research in deep learning and specifically in kind of understanding what's going on with these deep neural networks.
I find it hard not to be kind of mesmerized by that almost emergent behavior where you look at a single neuron and you can understand its behavior very clearly. There's kind of the biological analog. You're like, okay, this thing just takes a set of inputs, it throws weights on them, it does a nonlinear activation. And then you throw a bunch of them together and look at what it does. It's kind of fascinating just to have to think about how that could possibly occur. And so in your own journey, it seems like you kind of went from this initial, more applied interest. You wanted to look at predicting stock prices, and then you went over not all the way to theory, but I guess to what you've described as more empirical theory. Did you ever hold on to the more applied interests that you had when you just got started?
It comes and goes, I think. Yeah, so there was a sense, I guess, when I was working at Uber and at the same time I was kind of doing research on the side with some of the folks from AI Labs. And I really liked that in my research, it didn't matter if the thing that I was working on had any applied value for the company. Whereas in my job, I was working on things that had a clear impact. And so that's how I felt. That was something that really attracted me to research. This idea that you kind of just work on things that were intellectually interesting and that you're curious about. But then after doing that for 2 years, I'm like, wait, what's the point of this, right? There's this, I can understand the feeling of wanting to work on things that has value for people, has value for society, and a lot of times, really fundamental research, there's not a very clear connection to an application. So, yeah, I think it ebbs and flows. But for now, I'm kind of in the middle, I guess. I like to have my work, have the potential of being useful, but it doesn't have to be the starting motivation.
Empirical theory seems like a happy middle road. And at the same time, based off of what you were just saying, I often feel like there's a kind of bravery needed to engage in really deep fundamental research, just because of the fact that you're working on often really difficult problems that are about understanding things at a base level. And if you hit on the right understanding, if you do something there, there is a potential to make a really massive impact. But I think there's also that huge risk that you go down a wrong direction, that nothing ever happens. And if you keep yourself very much on the applied front, you, as you said, can more easily see a real life impact there. And so it's really, I guess, just a difference in terms of how the kind of delayed gratification you might be willing to endure, or delayed possibility of gratification and large risk of no gratification whatsoever.
Yeah, I mean, it is a good middle ground because, regardless of whether or not there's follow-up applied value that comes out of your work, is at least interesting to at least some people. So, like, if you gain some insight into how the models are working, even if it's not immediately clear how that may be useful, people are still interested because it's, cool to know these things. But yeah, if you're working on applied things and you're taking a novel approach, perhaps it doesn't work and then nobody cares about the product, right? So there is kind of, I think it's a good risk profile here. Yeah, I mean, it's the best, I think, research question is when, regardless of what the answer is, it's still going to be interesting. So that sometimes happens in this kind of empirical theory, understanding deep learning type of work.
Yeah, it definitely seems to be the case. So while you were at Uber AI Labs, you worked on this really interesting paper Deconstructing Lottery Tickets. By way of introduction, do you want to tell me a little bit about what the lottery ticket hypothesis is in the first place, and then what you were looking to learn about it in this paper?
Yeah, so the lottery ticket hypothesis states that within a randomly initialized neural network, there exists a subnetwork that, when trained in isolation, can achieve the same performance as the full network with, all of the weights. So practically speaking, this means that you can kind of prune the network, have a sparse model, and just train the subnetwork and still get the same performance. And this is really interesting because one, it suggests that maybe there's some efficiency gains that we can have from only having to train, fewer weights and, have save on training costs and inference costs. And the other reason it's interesting is that it provides a perspective on why overparameterization might be helpful in neural networks. So the idea is that when you have a lot of parameters, you have more chances of having a lucky subnetwork within that model that just so happens to be a good starting point for this particular task that you're trying to learn on. So that's why it's called a lottery ticket. This subnetwork is a lucky initialization, and perhaps that's what's driving the training trajectory of the model when you train the full model. So that's kind of a cool hypothesis for why overparameterization might be helpful for deep learning. The question that we were trying to explore is what is going on here. Basically, so in the original paper, they showed that you can identify these lottery tickets by doing something called magnitude pruning, where you train the full network first, and then you keep only the weights that have large magnitude at the end of training. And that constitute your lucky subnetwork. So you rewind those weights back to its initialization and train just the subnetwork. And you see that you can achieve the same performance. So it opens up a lot of questions like, why is this simple method of magnitude pruning able to identify these lottery tickets? What makes these lottery tickets good for training? And yeah, can other ways of identifying lottery tickets also work? So a lot of questions about basically what's going on here, what's responsible for the results that were shown in the original paper.
The initial picture of overparameterization you were talking about, I think, presents kind of two interesting views or things to look at. So one would be the view of overparameterization in that you have part of the network, perhaps your lottery ticket, that is doing most of the useful work in a network, really capturing what information you need to get out of the data. And then you had this kind of excess capacity left over. And sometimes it seems that this tends to act as something like a lookup table, perhaps memorizing difficult examples. And I think there's related work that's shown the way in which many pruning methods actually causes networks to, while they might improve in performance overall, the sets of inputs, sets of examples that they do well on or degrade in performance on, there's kind of distributions of what's going on there, right? And I think there's some relation to your work here. There's also kind of the interesting view that you mentioned of initialization, of these lottery tickets as a lucky initialization. And I think that recently we've seen a lot of views of pre-training as just providing good initialization for these large language models. Have you kind of spent time delineating some of those connections?
Yeah, so I think, obviously the lottery ticket initialization is different from one that you might get from pre-training. So part of the perspective, I guess, that came out of the Deconstructing lottery ticket paper is that the initialization, the subnetwork that you identify, actually contains some information about your data set. Because the way you identify that subnetwork is through taking information from a training process. So in some sense, it is related perhaps to a pre-training initialization, except, right, in this case, it's kind of on the same task as your downstream task. So yeah, I guess like if you have an informed initialization that has some good general features that are already present, it helps you go down a learning trajectory that maybe leads to better generalization also. And I think this idea also comes up in, the fortuitous forgetting work that maybe we'll talk about after. This idea that you can start from successfully better initializations, and that can help you kind of amplify what good features are contained in these initializations. So yeah, maybe there's some high level relationships here, but yeah, I haven't thought too deeply about that.
Sure. So in this work, when you were investigating these concepts of rewinding, you look at some different types of masking. I think you labeled them type 1 masking, type 0 masking, if I remember the labels correctly. And you sort of study the effect this has when you kind of rewind networks, when you apply these masks to them. And you make this really interesting claim at one point that, quote, masking is training. Can you tell me a little bit about the study of masking that you did here and then what you meant by that claim in the paper?
Yeah, so a really surprising thing we found while we're doing this investigation is that not only are these subnetworks, these lottery tickets, good at getting to a good final solution when you train them, they're actually already good at initialization before you do any training. So if you think about this lottery ticket training procedure, you first train, say, the dense model to convergence, and then you look at the magnitude of the trained weights, and you set the weights with small magnitudes to 0. You prune those weights, and then for the remaining weights, you rewind them back to their initializations. So if you just measure this network at initialization after doing this rewinding and pruning, we found that the accuracy is actually already better than chance. So at initialization, the subnetwork is already containing some information about the task. And so why would that happen, right? The only thing that we changed is to apply this masking procedure by setting some weights to 0. So the interpretation we had was that, okay, the weights that we're setting to 0 are weights that ended up with a small magnitude if you train the full model. So in a way, for these weights, by masking them, we're moving them towards the weights, the values that they would have gone to anyway if you had trained them. And so this is what we mean by masking as a training step. Both that, it makes sense based on kind of where we're sending the values to. It also makes sense based on the impact that the masking procedure has on sort of the randomly initialized model. So yeah, that's kind of what we mean by that claim. And yeah, I mean, it has some interesting implications, I think. So one implication it has is perhaps on this hope that people have about, okay, maybe we can identify subnetworks or lucky lottery tickets at initialization without having to do all this expensive training and pruning process. But maybe this perspective suggests that you could only find the subnetwork after you've done this training process, because the pruning itself is part of the training. So, it doesn't preclude the possibility of being able to identify lottery tickets at initialization, but it suggests that maybe this is going to be harder than we think. The other interpretation that I think is not very common or not very intuitive for people is that we typically think of pruning as removing weights that are useless. We're deleting these weights from the network. But our experiments kind of show that the weights that we're setting to zero are not useless. In fact, they are useful at the value of zero. So your the subnetwork that remains is working alongside the subnetwork that you set to zero, and they have to be complementary to each other. And I think this is the reason why, if you say randomly reinitialize the weights of the remaining subnetwork, it's not going to work as well. And also perhaps why it explains why the lottery ticket subnetwork will train to the same basin as the original network. So they'll train to a similar solution or solutions that are linearly connected. And you can kind of intuitively understand that this is because, part of the weights are kind of already locked in. So you're locking into a solution path because all of these weights are now set to zero. So I think those are some interesting, implications of this perspective of masking as training.
One thing I'm curious about when it comes to the setting weights to zero is what the picture might look like for really large networks or larger networks than you were looking at when trained for a really long time. If you were to start looking at the long-term training dynamics, and things I have in mind are like model interpolation, what happens beyond that threshold. If I remember correctly, you were studying this on CNNs that were like 2, 4, and 6 layers, right? And so if you look at a network that's trained for a really long time, one thing I can imagine in line with the idea that perhaps a model over its training evolution perhaps forgets things, but then it also relearns them, kind of not so subtly, making reference to another paper we're going to talk about soon. But at some point in training, maybe a set of weights start converging to zero, but then later in its training dynamics, it realizes, oh, wait, these were actually important for something or the other. One thing I kind of have in mind there was the study that I think Bean Kim and a few others did of the training dynamics of AlphaGo and the way it kind of discovered and then forgot concepts along that training. But anyway, I guess what I'm wondering there is the masking says, okay, these weights are going to zero anyway, so let's just actually set them to zero, accelerate part of the training process. But you could imagine that if you were to train a sufficiently large network on a sufficient amount of data for longer, perhaps at some point in training, those weights become important. Is that something you could imagine happening or that you'd have any intuitions about?
So during training, I guess if you looked at the individual trajectories of weights, they're not going to be monotonically kind of moving towards their final position, right? If we're thinking of the idea that these weights are moving towards zero, that's not kind of how it happens during the training process. So, and the other thing is these weights are moving towards zero, but they're not actually zero, at least, at the end of a dense model training. And that kind of maybe changes, right? So the remaining weights are not going to end up in the exact same values as they were before in the dense model. So I think definitely the weights, individual weights may not have too much meaning, but they're definitely kind of going in different directions throughout training. And you have to do that for the whole network to kind of adjust itself as it trains. And yeah, I mean, there's definitely like information being forgotten and relearned throughout training too. Like if you look at the performance on an individual data point, you can see that the model could at some point learn to classify this image, but then later on forget again and then relearn that. So it's not super clear how this mechanism works exactly. There is actually this interesting observation from the LCA loss change allocation paper that showed basically just over half of your parameters are actually helping the loss at any given training iteration. So there's also a lot of noise that happens during the training process. So what I mean by that is every step that you take with gradient descent, you update all of your parameters, and only half of those updates are actually contributing to a reduction in the loss. And the other half are like moving in the wrong direction, essentially. So yeah, I think there's just a lot of like noise and movement and adjustment that we don't quite understand during the training process.
Yeah. One thing you had also mentioned earlier was the fact that we can do this masking, we can identify these subnetworks that are useful. It's something we can only really see after training, this kind of a posteriori knowledge. And as you said, it does make one wonder, what if there were a way to identify these things before we kicked off the training in the first place? And that's not really something that this research makes a claim on in one direction or another, as you were kind of mentioning. But I'm curious if you're aware of any work or have thought further about that possibility.
I think there were many papers that tried to do pruning at initialization by maybe, for example, looking at one-step gradient direction of the weight updates and using that information. But then there was a paper that kind of looked at all of these proposed methods and compared them to a version where you just shuffle the weights. So basically, if you've actually identified a subnetwork that is particularly good, then if you shuffle the weights, that should no longer be good. But it turns out that it is. Basically, like the performance is indistinguishable from some sort of random subnetwork. So that kind of is suggesting that maybe none of these methods are doing really anything more than something you can do with just random pruning, or like a clever version of random pruning. I haven't seen anything recently that had better performance on these things, so it seems like maybe this is just a really hard problem, or maybe this is kind of not the easiest way to be doing more efficient training, I guess.
That's fair. Let's talk about the next section of your title. So the sort of subtitle there was zeros, signs, and the supermask. So we talked about zeros. Now, another thing you investigated was the role of signs, and I think that you found in this rewinding of neural networks that you did to their initialization, the sign of weights was actually more important than the magnitudes. Can you tell me a little bit about that study and what you learned from it?
Yeah, so we wanted to know what about this lottery ticket initialization is useful. And so we decomposed the values into just the sign or just the magnitude, or sign and the magnitude. And we basically try to keep each of those components and retrain the subnetwork and see what we get. And we found that just keeping the sign was enough to get kind of comparable performance to the full lottery ticket, and also the full network, which suggests that what was critical to keep in these subnetworks is just the relative signs. The magnitudes don't matter so much. And this suggests kind of that maybe, so we talked about this like basin of attraction idea for the solution that the model eventually get to. And it seems that, the model isn't super sensitive to the exact initialization values. It's able to get to that solution with just the right sign of the weights, suggesting that, maybe the basin of attraction is pretty large and the model isn't super sensitive to perturbations in the initial conditions, or at least this particular form of perturbation, which is like changing of the magnitude. So that was really interesting.
The idea that the basin of attraction, I guess the size of it could be pretty large, is interesting. And I guess one thing, I can't remember how many different sort of magnitudes of initializations you tried in your paper, but I'm sort of curious how that would work out. So if you were to keep perhaps the relative weights or the relative magnitudes of the weights you initialize the same, along with the signs, then kind of how far you can go in terms of messing with that, but then still achieving better than chance performance.
Yeah, so the first time we tried this, we just set all the weights to like 0.1. And that just like already worked. And at least for, the simple MNIST experiment. And in the paper, we ended up setting it to a value that was like proportional to kind of the initialization that I don't think it would work. For example, if you set it to a really large value, so it is still sensitive, but within like a reasonable range of what normal initialization values are, it seems to, all kind of work. But this still depends on the particular task that you're looking at. I think maybe for more complicated tasks, especially tasks that are more complicated compared to the capacity of your architecture, it may be the case that it becomes more sensitive to the initialization values, and maybe then the sign isn't going to be enough. But for the experiments in this paper, it was enough, and sometimes like even slightly better. For I don't know why that happens.
I can see that intuition, how the sensitivity to the magnitude could possibly depend on, as you said, the match between the network capacity, the problem difficulty.
I think it's probably also related to the stability idea that was explored in, I think, the follow-up paper, Lottery Ticket at Scale, or maybe they changed the title, where, it wasn't enough to rewind to initialization for larger data sets and larger networks. So basically, if you scale to ImageNet, the original experiments don't hold anymore, and you need to rewind to the weights after a few epochs of training. And they were looking at this from a stability perspective early on in training, and they found that for these larger data sets, it's more unstable early on, so you want to kind of skip that unstable period. And I suspect this is related to stability, so like how much precision you need in the weights is also related to how stable the training dynamics are. And I think that's probably dependent on the data set.
That makes sense to me, and I can see that relating to the basin picture that you've been talking about. The fact that over the first few epochs for a sufficiently large data set, you're not really in a regime of training yet where you've encountered enough of it to have a good, statistically valid, for some very loose definition of that phrase, picture of the data generating distribution. But then after a few epochs, you do get within some region of the solution space, of the solution basin, that now your training dynamics are going to be a little bit less haywire and probably leading you into something like the right direction when it comes to having weight magnitude signs that actually correspond to what you're eventually going to be looking for.
Yeah, I've heard that, in some experiments the sign observations don't hold, but then in some other ones they do, like as people try to scale up these things. So yeah, so that's my guess at what's happening there.
Tell me about the Supermask.
The Supermask is probably my favorite idea in that paper. It's building on top of this masking as training thing. So we found that the mask that you get from magnetic pruning results in a network that is better than chance at initialization. So without any training of the underlying weights. And so we kind of refer to masks that have this characteristic. Supermasks, basically, it suggests that, perhaps not only do randomly initialized networks contain subnetworks that are lucky initializations that can train to good performance, they contain subnetworks that are lucky enough to have good performance on your task without any training. So it suggests that, within some randomly initialized network, you can find a subnetwork that performs well already on the task that you're interested in without training the underlying weights. So that's the idea, and we showed, a couple heuristics to identify these supermasks, and also one method of actually training and learning to find these masks. And it's really interesting because, first of all, it suggests maybe an alternative approach to training neural networks. So instead of training the weights, you can do a search over subnetworks of a randomly initialized model. The other cool thing that sort of is not really mentioned in the original paper, but that I'm most excited about nowadays, is using this idea of masking as a way to probe a pre-trained model. So the original Supermask idea applies the mask on untrained weights, randomly initialized weights. But you can also do this on top of any kind of frozen set of weights, including a pre-trained model. And you can try to find maybe subnetworks within that model that is responsible for certain characteristics, or for learning certain features. And that's something that has been somewhat explored in follow-up work, and I am quite excited about that direction.
That sounds really exciting to me too. The first thing I wanted to comment on, though, before maybe talking a little bit about that, is the picture you just presented of having, again, lucky subnetworks and these supermasks as being able to identify ones that at initialization are better than chance. Intuitively, speaking to the picture of luck you mentioned earlier, I guess you would imagine that a more over-parameterized network is going to have more luck, as it were, if you were to perhaps hold the data set fixed or something. And to the search thing you were mentioning, there's that kind of interesting double view you now have of perhaps a sufficiently over-parameterized network, where on the one hand, it's just, I'm training this massive thing that is going to probably overfit to memorize aspects of my data set, or you could view it as this really big network in its training, sort of doing an architecture search over the subnetworks that already existed within it.
Yeah, I mean, that's a really interesting way to phrase it. I think there's some theoretical work that kind of proves that with, a sufficiently over-parameterized model, you can always find a subnetwork that works well, and the intuition is exactly as you're suggesting. Like, with more weights to choose from, the chance that one of those combinations is good is going to increase as you increase the weights. it's also potentially interesting. I don't think this has been established, but potentially interesting way of providing a regularization to the training process if your training process was this mask search instead of training the weights. Because now there's only a few ways, right, that you can update the network, and that could provide some like interesting generalization properties. But I haven't really seen this being explored. But this is like, yeah, one potential difference that may come out of this different type of perspective on training, going from like weight change to just like a search over a random space of subnetworks.
That's something I'd be very excited to see someone study. The other thing you were talking about that was really cool was this idea of masks as a way to probe pre-trained models, perhaps for specific parts of the model that are responsible for interrogating certain characteristics of the input data. And that certainly connects, I think, to other work that has investigated ways of steering models or intervening on the concepts and things that they sort of look at. So I know that concept bottleneck models was one work from a couple of years ago that looked into this. And then we've also seen some more recent work that's looked into steering pre-trained large language models, just in sort of certain directions, perhaps based off of the difference in weights between like a fine-tuned and then a pre-trained model, which I thought was really cool. And so I'm curious if you have any thoughts on just what it would look like in terms of, or I guess you were mentioning that people are starting to kind of explore this, right? Of masking as an additional way to intervene on these pre-trained large language models and sort of steer them in particular directions in terms of perhaps desirable, undesirable behavior, things for them to pay attention to.
Yeah, so I haven't seen people do this on large language models, but I would love to see it. But what I have seen, so there's this really cool paper called Supermask and Superposition. And the idea is that basically they're trying to tackle this problem of catastrophic forgetting in continual learning. So essentially, if you want the model to kind of continuously learn multiple tasks, it tends to forget about the tasks that it learned earlier on when it learns a new task. So this is kind of referred to as catastrophic forgetting. And the solution in that paper is basically you take kind of a pre-trained model, maybe trained on a large data set, and you have these downstream tasks that you want to specialize to. And instead of fine-tuning this model to each of those tasks, you find a mask that, when applied to the pre-trained model, generates good performance for a downstream task. And, you can do this because, again, masking is a form of training, right? So it's possible to train a mask towards like a different objective. And so you can have a mask for each of your downstream tasks, and you will never have the issue of catastrophic forgetting because the underlying weights are never changing. And so at inference time, you can have some sort of clever heuristic to identify which mask you should be using. But this is really cool because it's kind of like this idea that the pre-trained model, maybe has a store of many different features. And by selecting different combinations of these features, you can adapt them to and specialize them to a different task, just by kind of choosing a subset of the connections that exist within this model. So this is a cool perspective, I think, on and why I'd be excited to see this in large pre-trained models, because you can imagine that story holds for large pre-trained models having all this like overlapping knowledge about things, but maybe they kind of interfere with each other when it comes to a specific downstream task. But if you can remove things that are interfering and uncover the right combinations, you can get good downstream performance. So that's something that I was really excited by.
Yeah, the interference phenomenon is tricky, and I know a lot of people are working on that. It's kind of interesting, though, the picture you just presented, because you can think of that multitask learning or having a single multitask network as like architecturally just a picture of you've got this backbone, you get your representation, and then you have a couple of task specific heads. But then in this case, now you've got sort of a full, perhaps end to end network or something like that. And then the picture you presented at inference time is like the task specific heads are really just these masks you're now applying to the network instead of something that's kind of lopped onto the end of it.
Yeah, I think, yeah, that's a good way of putting it. It's like some particular path through your whole network that is like good for this task rather than, a new set of weights or a new head. Yeah, I think there's some elegance to this if this is the true picture, which, I don't think we've proven that, but yeah, it's interesting. There's also another paper that looked at kind of applying a mask on the trained model, but on the same task, so not looking at a downstream task. And they found that when you kind of use this subnetwork that you identify, and I think then also doing retraining, so almost using masking as a pruning technique, like to find a lottery ticket, what you end up having, the model that you end up having has better out of distribution generalization performance. So that's also interesting. It's kind of like you've identified kind of the core of the original model that was responsible for the good performance and kind of stripping away the other things that may be contributing to overfitting to the training distribution. So, I mean, this is sort of hand wavy, but that's like a cool application of training a mask for, some other purpose.
Yeah, intuitively, that does seem to make a lot of sense. One of the phenomena that you mentioned in regard to this was catastrophic forgetting. I will use that as a not so subtle segue into your work on fortuitous forgetting. Can you tell me a little bit about what fortuitous forgetting was and what you were getting at in this paper?
Yeah, so the idea is that, for humans, forgetting, even though it has a bad reputation, is actually a very useful process that our brain does to aid in learning. So there's a lot of evidence in cognitive science that show that forgetting has a symbiotic relationship with learning. And the question that we're wondering about is, can the same be happening in artificial neural networks as well? And we were seeing several different works that do this kind of iterative training procedure to get better generalization or better compositionality and things like that. And we try to figure out if there's some common reason that all of these algorithms that are proposed is beneficial, because all of them kind of have some speculation for why they work, why they contribute to better performance, but it's not really proven. And so we wanted to see if we can unify the picture for all of these different algorithms. And the hypothesis that we came up with is this forget and relearn paradigm, which is a type of training process that comes in stages. So it's an iterative process. And in each stage, you have a forgetting component and a relearning component. In the forgetting component, you try to remove some undesirable information from the model. And then in the relearning component, you try to retrain the model towards, your desired objective. And you do this iteratively. And so the hypothesis is that when you do this, every time you retrain, you're starting from a better initialization that has less of the undesirable information and more of the desirable information. And you can build, you can iteratively amplify the desirable information within the model. So this can give you a way to steer the model towards desirable characteristics. And I'm using these words very loosely, but that is the kind of high level idea here.
Sure. One of the things you mentioned was the relationship to some other work. And there was one that kind of got me thinking about the representation learning perspective on what's happening here, which was, I think it was called Rifle, where you mentioned that they were able to improve transfer learning performance by periodically reinitializing their final layer during fine tuning. And then this kind of led to updates to low level features in previous layers. Can you tell me a little bit about if that kind of got you thinking about any questions and sort of that representation learning perspective on this as well?
Yeah, so we also have some similar experiments in the paper that doesn't apply to transfer learning, but does reset the later layers of the network. And I think one of the questions there is, when you reset the later layer, what is causing the improvement after retraining? Is it that you now have a better later layer because this later layer, like let's say the last layer, is now trained on top of better features in the earlier layers? And so you're able to, through reinitializing and retraining, improve the features in that layer. Or is it the case that the features that are in the earlier layers are being kind of amplified because they're never reset? So they're continuously being improved every time you do this reinitialization and retraining of the last layer. And so those features get stronger and stronger. And we set up, several experiments to test this. And the answer we concluded was that the second perspective seems to be the right one. So the features that are in the earlier layers are more general, and they are basically being kind of amplified when they're continuously trained. So kind of similar to you mentioning that now basically there's signal propagating back to the earlier layers more than, kind of a fully trained model that has low loss and small gradients. So the other kind of subtlety here is that when you reinitialize the last layer, you're providing a new environment for the earlier layers to adapt to. And basically features that are easy to adapt to many of these environments intuitively is more general as well. So that's kind of another motivation or intuition for why these earlier layers are becoming better generalization and better features.
That makes sense to me. In reading this paper and thinking about the training dynamics of a neural network over time, one connection that kind of arose to me was the overlaps between your work and then other recent work that's studied neural net training phenomena. And in particular, what I had in mind was double descent, grokking, the information bottleneck paper. So I'm curious if, in sort of looking at that other work, whether you've thought about the connections between the forget relearn phenomena that you looked at on one hand, and then in, for example, double descent, the idea of this interpolation regime and what's going on there.
Yeah, maybe we can start by saying that the grokking phenomenon sort of maybe is almost an example of potentially all three, even though that's not necessarily established. Basically, in grokking, there's a delayed generalization behavior. So your training accuracy goes up, let's say to 100%. And at this point, your test accuracy is still 0 or close to 0. So there's no generalization. But if you train for a really long time, suddenly the test accuracy goes up. So yeah, so basically, and I think you can maybe see a double descent shape of some of the training curves in these experiments. One perspective is that over this long training, like after training losses or training accuracy is 100, the model is basically consolidating in some sense, or maybe simplifying, or maybe finding the best fit of the solutions that fits the training loss or training objective while moving towards some inductive bias that the training procedure has. So it's constrained by, as you move through the weight space, it's constrained by having to still keep a low loss, but it's doing something else. So one thing it might be doing is that when you use weight decay, for example, when training loss is low, I think weight decay will then kind of be primarily responsible for the movement of the weights. So in a sense, you can imagine that the network is simplifying during this regime, and you can kind of connect that to the idea of forgetting. So like removing information that is not critical for doing well on your training set. So yeah, I think maybe there's like some connections between these ideas, and actually for grokking, if you had applied the forget and relearn procedure on that, you do see grokking much faster than if you have normal training. So this is really interesting. It's not direct evidence to say that normal training is doing something that is similar to forgetting and relearn, but at least both of them kind of achieve a similar outcome. But I think the connections haven't really been well established. But yeah, there's some interesting questions there.
Sure. The inductive bias picture is really interesting too. There's a great blog post from a while ago on double descent called Inductive Biases Stick Around. And I think it makes the claim kind of at a high level where very early in the training of a neural network, the inductive bias sort of matters. But then as you kind of get into this pre-interpolation regime, that starts to go away. And now you're in the regime where it's kind of all just looking at the data. But then once you pass that regime, you come back to a point where, as you said, the inductive bias starts to matter again, which I thought was another kind of really interesting way of looking at that phenomenon.
Yeah, I don't know how to sort of establish that as the actual explanation for what's happening. I think it's quite difficult. But I would be curious to see if, people are able to draw a connection to information bottleneck, right? Because in that theory, they do say that when you train, for a long time, what's happening is that the mutual information between your representation and the input is decreasing. So in a sense, it's like removing information from the model. And yeah, that was supposed to be helpful for generalization. So I do wonder if it can explain some of this grokking behavior as well.
Yeah, there's a lot of cool work that I think explicitly establishes generalization bounds based off of like input output mutual information. And I know there's some like really heavily theoretical stuff. Like there's this Shu-Roginski paper from I think 2017 or so that does this. Very theoretical, but I think there are some important overlaps there. There's one final bit on this paper that I wanted to ask you about, which was in the final part of the conclusion. You discuss this idea of features that are consistently useful under different learning conditions, and you note that the iterative training process that you do in this paper is pretty expensive, and so there's this open question of could we develop algorithms that capture the same benefit without this iterative training process? And I'd love to know if you have either seen work investigating that or have any intuitions on what such a training scheme could look like.
Yeah, that's a good question. I haven't really seen anything that tries to replace an iterative process. I've seen instances where you actually don't need an iterative process. Like you're able to just forget the right information and you don't have to keep doing this. You can do it in one go. And I think maybe it's questionable whether it's a worthwhile investigation to figure out maybe a complicated way of getting at the same benefit, because this is almost like another lesson from scaling, right? Like the iterative process is kind of taking something that works and just multiplying it and almost bootstrapping the process, and it's easy. And so yeah, I think we're seeing a lot of examples where if it works, it's kind of like, especially with the absence of clear alternatives, it's actually not that bad. I think at the time of writing the paper, I really didn't like this aspect, but now, I think, even in large language model field, we're seeing a lot of these iterative improvement approaches that I think is really interesting. And I don't mind that they're doing this iteratively, right? So for example, you have like papers that have the model generate some labels for the data set, and then you fine tune the model on those labels, and then you generate a new set of labels that are now hopefully a little better because the model is better. So that's an iterative process that you can use, and I think that's actually quite elegant. So now, yeah, so this isn't a direct answer to your question, but this is my current feeling about this idea of an iterative refinement, which is actually quite deeply interesting as a paradigm of improving models.
I think that's pretty fair. And in general, I guess what seemed to us to be large or expensive just a few years ago no longer feels that way now. So I do think that's a very fair perspective to have. In the regime of large things, you have another paper, very recent, very exciting, teaching algorithmic reasoning via in-context learning. And I have, I guess, a question wrapped inside another question to kick this one off, which is, I guess, a standard what is in-context learning, but perhaps around that. What I note about the title of your paper is that the phrase teaching algorithmic reasoning really aspires to something, I feel, that sort of goes, it takes what you did in this paper as a starting point, but the aspiration kind of goes a lot further than that. So I'd also love to hear about the sort of broad vision for you and what you hope will follow from the initial work you did on algorithmic prompting in this paper.
Yeah, I mean, it's true. We definitely had more ambitious visions for where this could go, but of course, that's yet to be realized. So to start, what is in-context learning? Basically, with large language models, what it can do is completing the next tokens and completing sentences and paragraphs. So you can start the model off with a prompt or a string of text, and the model is going to complete from that starting point. And what people have found is that you can provide information to the model within this prompt about a task that you want the model to do. So one way to do this is providing a few examples of input and target for this task, and then append these examples with a test question that you want the model to answer, and the model is seemingly able to pick up on how to perform this new task from only seeing what you're providing in context, which is this prompt. So that's what people refer to as in-context learning or prompting. And it's really exciting because it's a very flexible way of controlling what you're getting out of the model. And it's really exciting because you can teach or maybe get the model to perform these tasks without having to change the underlying weights of the model. So the model itself can stay general, and it can just interface with it to get, new behaviors out of it. So in teaching algorithmic reasoning via in-context learning, we try to see if we can actually get the model to perform algorithmic reasoning by teaching the way to do that through this prompt. So the testbed that we are using is arithmetic because it's kind of been long observed that these models are still unable to robustly do simple arithmetic questions. So like addition, as the number of digits increase, the model accuracy on these questions will drop. And so we try to teach the algorithm for addition by showing the model examples of applying this algorithm and then ask the model to kind of do the same thing. And we found that the model is actually now able to generalize out of distribution to questions that are much longer and harder than the examples that we've provided. So it's showing that the model is actually solving this problem using the solution strategy that we've defined for it, which is why we're calling it teaching. Although, I think that term kind of doesn't sit well with some people because it's in context learning. There's no change to the model, but we do find that the model is actually using what is provided in context rather than using some of its pre-training knowledge to directly solve the problem.
There are a lot of interesting pictures of that, and I guess the very basic picture of in-context learning is I have a task I want you to solve. Here are a few more pairs of inputs, outputs of this problem solved. Now, here is a new input for you to look at, solve the problem, do this analogy, provide me this summarization. And so you are now looking at these kind of diametrically, maybe not diametrically, but these kind of opposed things of, on the one hand, discover an input-output mapping, the in-context learning picture, but then I want you to do algorithmic reasoning, i.e., mechanistically applying a procedure that should be input independent. Can you tell me a little bit more in detail about that prompting strategy, what that looked like? And I suppose for the test bed that you used for arithmetic, what it meant to provide your model with a demonstration or an explanation of what was going on that was non-ambiguous enough for its behavior on new training or on its testing examples to be a little bit more mechanistic in nature.
Right. So in order for the model to perform algorithmic reasoning, like you said, it needs to be able to kind of generalize mechanistically, generalize by actually following the same rules to a new test example outer distribution. And the fact that, we were able to do that with whatever prompt, right? Just the fact that the model is capable of exhibiting this behavior is really interesting. And I think this actually points to the bigger picture that we were hoping to start with this work, which is just this idea of like, can we treat language models as students in school, where we can kind of teach these skills to the students and build on top of these skills, because the model, have shown, we've demonstrated that the model has kind of these underlying capabilities of learning these kind of skills and doing this kind of reasoning. So that's sort of where we're hoping to go. But in terms of the actual strategy that we use, basically imagine someone explaining to you how to do addition. You would start with the rightmost digit, add them up. If there's a carry, keep track of it, and then move on to the next digits. And when you're taught this in school, you're given like, here are the actual steps that you need to do. Here are the equations. This is the addition equation that you need to use for each of the digit sums. And a lot of times with language models, people don't go into that level of detail when trying to get the model to do something, because it feels like this is obvious, right? If I say add up the two numbers, you should know this is what I mean. If I say, keep track of the carry, you should know the carry is 1 when the sum is greater than 10, 0 otherwise. But I think this is assuming a lot about the, bias that the model has to interpret these sentences. So the idea is try to provide as much detail to disambiguate what we mean by each of these steps, so that we can have more of a robust behavior from the model and get it to do what we want. So yeah, I guess that's sort of the motivation, right? So if you, for example, show the addition algorithm by just showing, for each step, the carry value here is this, without explaining how that carry value is derived. With a limited set of examples, there are many valid potential rules that could explain your observations that you provided. So I think in a way we can't really fault the model for not doing what we want. And we found that, when you have very explicit demonstrations, the model is able to pick up on the pattern and actually flexibly apply them to new situations.
The picture of in-context learning as a phenomenon felt kind of mysterious when it was first being observed, and I know there's been work since then studying what exactly is going on. I'm curious if your study of algorithmic prompting and in-context learning so far has given you any intuitions on what exactly is happening within context learning.
Yeah, I think one interpretation I really like is the induction head hypothesis from Anthropic, which is kind of saying that what is happening in context learning is that at the current token output, the model is looking within the context for a pattern that is similar to the pattern that's immediately before the current output, and looking at what came next in that previous example, and then outputting something that is similar. And so this is kind of what they call an induction head. And you can do this in abstract ways, right? You don't have to find an exact match. You can kind of find a similar match by some sophisticated, metric. And I really like this, and I think the success of algorithmic prompting, and in particular the importance of having demonstrations and not just descriptions of what you need to do, but actually showing it in examples, kind of leverages that idea, because now we've converted the question into, well, we've essentially converted algorithmic reasoning into a pattern matching question. So now the model has to, at each step of the output, find something in the prompt examples that looks similar, see what happened there next, and kind of apply that same relationship. And we know models can do this, right? We know models are good at pattern matching, and having these demonstrations also makes this process easier, per the induction head hypothesis. So if you only had instructions, it would require a much more abstract similarity metric to get to the same answer. So yeah, I think I really like that interpretation because, it seems to explain some of why algorithmic prompting is so successful in doing these kind of outer distribution generalizations.
There is a cool natural link there. Another series of papers that I found kind of neat recently has been the ones that are trying to establish this relationship between in-context learning and gradient descent, which is a really interesting picture because in-context learning, it feels like, well, literally you're not updating the weights of your pre-trained model anymore. And so in one picture that's like, well, even if I have a new task, it's able to do that well, quote unquote, without further training. But some of these works did this really interesting set of derivations to look at like a dual form between gradient descent and then linear self-attention. And then they kind of take that linear self-attention picture forward and understand in context learning as this kind of implicit fine-tuning where the transformer attention is like doing a meta optimization. And then in its forward pass, it basically is implementing gradient descent. And so there's kind of a weight update going on there. And I guess the big difference though is that the pre-trained LM is producing like meta gradients according to the demonstration examples through its forward computation. Whereas of course in fine tuning, you are actually getting like real gradients through the back propagation process. But it's a simplified picture, but it seemed kind of cool to me. At the same time though, in thinking about your work, the fact that it's not just a set of inputs and outputs, which I think is the most natural version of in-context learning to look at for this gradient descent picture. You're also providing like explicit instructions in your prompts to make them non-ambiguous for a model. I guess it felt to me like the gradient descent picture, at least as it currently stands. I'm curious how it'll evolve, but the current picture felt a little bit insufficient for understanding what's going on in the algorithmic prompting that you're doing.
Yeah, I haven't dug into the detail of that work, but the idea that you can kind of draw theoretical connections between the two seems really cool. So I'm excited to see how people are able to kind of further establish that connection. For me, the intuitive picture, which is kind of the one I'm trying to illustrate maybe with the algorithmic prompting for what's happening with in-context learning or what's happening with prompting, is essentially, how are these models trained? It's trained to kind of output the most likely token given a previous string. So when you're just training on, a large corpus of natural language information, there are many reasonable next tokens that could come, or many reasonable sentences that are maybe equally likely. And I think what maybe intuitively, what we might be doing with providing a prompt is to constrain the potential options that make sense, that are likely for the model. So now the model has to output something that's likely given all of this previous information, and that's going to really constrain the space of possible outputs. And I think the main goal with interacting with LLMs is basically, how do we make sure that the most likely output, per the training distribution, is the output that we want from the model. And one way we can do that is by kind of providing all this like constraining information so that the model's output has to be consistent with all of this previous information. Another way maybe you can do this is by doing this sort of fine tuning that people are doing, like instruction fine tuning, or things like RLHF. So basically you're kind of increasing the likelihood of certain type of outputs from the model. So I kind of think all of this are just doing this constraining process, so that we can get to the spot in the search space that is desirable for us.
One thing I believe you've commented on, it may have been in the paper, was the idea of algorithmic prompting as a possible strategy for discovering novel algorithms to achieve a task. And in what you're saying, there's this kind of trade-off between how specific you make your prompt, how constrained you allow your LLM to be, and then how quote unquote creative it can get in the techniques it applies to provide a solution to a given task. And so the algorithm discovery seems like, okay, let's loosen the reins a little bit and give it some creativity, and then see, okay, does this come up with some interesting procedure? And I'm curious if that's something you plan on investigating, or that you've thought about.
Yeah, so we actually don't make any claims that algorithm prompting will help with algorithm discovery. I think those are two different problems, and I don't think, like you say, the strategy is not meant for discovery. The strategy is meant for robustness and getting out of distribution generalization. So algorithmic discovery, I think, is a much harder problem. And so far what we have is just, if you were able to have an algorithm, the model can actually learn it and apply it, which is, a nice first step, but it's kind of not the hard aspect that maybe we want. And yeah, I'm interested in knowing how the models can learn to discover algorithms and can learn to generate hypotheses, and testing them. So yeah, maybe, the way to do that is by prompting it to do that, but it's not clear. I think the model just probably some sort of fine tuning, or some sort of fine tuning is probably required to get the model to be in this space where you're coming up with hypotheses. This is something that is not typically done, I think. A lot of the work that tries to kind of discover the right solution gets the model to output many possible candidates of the solution, and they try to like do something like majority voting or ensembling of the solution, which is, I think, a really cool approach, but it's not enough for what we want. It's not asking the model to generate hypotheses that then it can test. So I think there's some gap there between, current approaches that I think is an interesting research direction.
What's next for you in line with what you began investigating in this paper?
So what I just mentioned would be one possible direction. Another one is, we can try to push the limits of algorithmic prompting and see how, like, what other types of questions we can solve with this, where are the limits. But another question that I'm really interested in is doing sort of reasoning that are not rigid the way that algorithmic reasoning is, because that's sort of the one big area that this approach doesn't cover, right? The whole approach for algorithmic prompting relies on this robust and rigid template that the model can follow. So it kind of misses a whole other type of reasoning that we may want. So I'm curious to explore that. I'm curious to explore the idea of the model like reflecting on its outputs and maybe thinking about its output by reflecting on its output and maybe by being critical of its output and try to poke holes in it. So yeah, those are some general directions that I may be interested in exploring next.
You presented this algorithmic prompting work at the Math and AI workshop at NeurIPS. It seems like there were a lot of interesting research directions and papers this year. I'm curious what stuck out to you.
There was one paper that I saw that is actually kind of related to the forgetting stuff that I thought was really interesting, where they identified examples that were contributing to certain classes or certain categories of test errors. So training examples that were not good, basically. And then they did like an explicit fine-tuning process to forget those training examples. And they showed that they were able to improve those error categories that these examples are responsible for. So that was really neat. I was surprised that that works, that you're able to just like explicitly erase information from the models. And in general, I'm interested in like all of these papers that do these iterative refinement or iterative self-improvement of large language models. I don't remember if they were all, published at NeurIPS, but had a lot of discussions while I was there about this direction, which is really exciting.
Yeah, it seems like there's a lot of interesting directions for iterative training to go, and especially when you start getting on the scaling regimes, as we were kind of mentioning earlier, and you're dealing with very large data sets and very large training schedules where you have these like very different regimes of training and things going on. It's kind of interesting to imagine the different directions that might go. One thing I'm curious about is just as somebody who is engaged in this research, it does seem like most of the attention right now and most of the discourse is around things at a particular scale, language models of a certain size. And you also, though, have done research at a much smaller scale with like 2-layer CNNs, for instance. And it seems like there are still some very valid scientific problems that can be investigated at small scale. But I'm curious, just as somebody who has been going to conferences, publishing work, how you view the set of scientific questions that people are kind of willing to entertain right now, and whether there's anything that you find kind of under discussed or that you wish were paid more attention to that seems to be getting overlooked right now.
Yeah, that's a really good question. I think a lot of PhD students are probably having this crisis of trying to figure out where their research agenda fit in with what's happening right now in the field, where like these large models are getting crazy impressive performance, especially if you were working on things like, trying to find failures of existing models and finding tricks or ways of improving them. And you see that actually all of these failures goes away if you just scale. It can be, bring into question what are the most potentially impactful questions, which I think have changed because of what's going on with large models. So yeah, it is it is slightly disappointing now that like there's this convergence of what things are interesting. I think maybe that's not the best thing to do for the field. I think it's always better when people are exploring, really different ideas. So yeah, I mean, yeah. So for example, like something like compositionality probably will appear with scale, and so there's a ton of research that went into that maybe won't actually be useful, going forward. Um, so yeah, I think there is definitely changes in the landscape for interesting research questions. Stuff that's underlooked. I mean, I think maybe everything that's not language model related is probably underlooked these days. So I'm not really well versed in these topics, but I would love to see more that studies like interactions between agents or interactions between a population of models. I think maybe that is something that I don't see a lot of, but will become really important when we want to apply these things to the real world, where maybe they need to interact with other humans, or just like the potential of getting more out of like collective intelligence of agents or models working together, rather than like the current paradigm, which is sort of one giant model that gets bigger and bigger and does everything. Like, could it be that, a population of smaller and maybe more specialized models could achieve better output due to this like emergence of this like collective intelligence sort of dynamics. So that's something that I think might be interesting, and I don't really see um, being done very often.
Another semi-related but seemingly very important area of study, I think, would have to be the human model interaction component of things. Just what does it look like to imagine the system that you're looking at as not just the model itself, but this whole thing of the person, the interface they have with whatever model is being deployed in a certain scenario, and then the model itself, and kind of trying to design that whole thing from the interaction to the information passed between things. That also seems like a really kind of important, more expanded picture as well to me.
Yeah, that would be really important with all the startups that's going to come out now that leverages this technology. I think that's like the core problem probably that startups need to solve to differentiate themselves, is just how well is the human interaction experience. So yeah, that's definitely super interesting.
As perhaps a place to begin closing up, as somebody who is in the middle of a PhD right now, I guess it's a very interesting time, as you said, to be doing a PhD. I'd love to know just your perspective on the broad academic research publishing culture that we have right now, what your experience with it has been like, what you like and dislike about it.
Yeah, I mean, I'm not a huge fan of the publishing culture. I think, the number of papers that go on arXiv each day is just exploding, and I think there's definitely benefits to getting all of this, stuff out there. But there's also a lot of harms, namely, like, it's hard to kind of find good and useful and relevant information from large number of papers being published every day. And it's also stressful to be a researcher that now you think, okay, you're supposed to write a paper every few months. And, a lot of PhD students are in this boat where they have to publish papers, get them accepted into conferences in order to graduate. And that's maybe not the right objective or the right criteria to measure how well you are doing in your PhD. And I think it also encourages, obviously, working on research that's more short term, that's more in line with what most people are interested in, because that's the easiest way to get published. And that's, somewhat of a disservice kind of to the scientific field as a whole when people are not encouraged to explore alternative paths. So, and yeah, I also think the load on the reviewing process is so large that that process just is really difficult to get right, and that kind of generates a lot of wasted effort, and a lot of noise. So I think there's a lot kind of that is making the PhD process maybe more and more stressful for people. But on the other hand, I also don't like, the idea of potentially like working on a large project with a large team and actually keeping it all private and never publishing, in a way that's really attractive because you're kind of doing something long term, but being able to share your findings with the community is sort of the best part, I think, of being a researcher. It's like the most fulfilling part for me personally. So, so right now for me, I'm trying to find this happy medium where I'm doing some work that helped me kind of advance in my degree, but also trying to keep the motivation for doing things that are just interesting and curious and maybe not going to be very popular, at least for now, but could potentially like inspire some new ideas. But yeah, it's definitely a tricky time, I think, and I think maybe PhD doesn't make sense nowadays for a lot of people as well for these reasons.
It feels very difficult to have to manage that balance between having to kind of stay relevant, as it were, but then also wanting to work on those really meaty, probably long-term projects that you might want to investigate. I remember Yoshua Benjo, I think, had a post a while back. This was probably a few years ago now, where he, I think, entertained some of the same doubts as you do about the current publishing culture in ML. And his, I think, something towards a proposed solution was kind of this hybrid where journals kind of serve the, I guess, prestige-ish role that conferences seem to now, where they're kind of the main venues of, okay, I've published a work that seems to be valued by the community, and then conferences become more or less this more regular, perhaps something similar to what arXiv is now. So, you have this work that's in progress, you have some initial results, you have smaller things that you've done and want to share them with the community. And so you kind of retain those benefits. I figure there are reasons why that hasn't happened yet. And I think it's a lot more difficult than just declaring, I want things to be this way. But it would be kind of interesting to see the publication culture move in that direction. And I am curious how Well, it does feel like something that might help promote the kinds of incentives, the more desirable incentives that you're talking about, allowing people to spend time on those problems and it kind of being accepted that, okay, journals are really the venue of publication. And since they have that longer review cycle, it's like okay to be publishing at a cadence of a paper a year instead of a paper a month or something. But it seems like there's a gap between where we are now and something a little bit more idealized like that.
Yeah, I think part of the problem is, or maybe twofold. One is there is a lot of people doing deep learning research, and so the field moves very fast, and so that just gives you a time pressure, especially if you're working on stuff that a lot of people are interested in. If you are not done with your project in, a reasonable time, probably someone else would have done it. So yeah, so that part I don't know how to fix, right? Because that's kind of the thing that's inherent in, like, if you want to work on this topic and a ton of people are interested. And yeah, this like prestige thing is unfortunate byproduct of having a lot of opportunities available that are like, high paying jobs or, prestigious kind of positions to be in if you have good publications that incentivizes people wanting to get their papers like reviewed and selected, and that like means something. So yeah, I think there's some like systemic issues that make it hard to just change the conference process or the review process, but I'm not sure how to alleviate those things.
Well, on that happy and certain note, I think this is probably a good place to close up. Well, Hattie, thank you so much for taking the time to do this with me today. I really appreciate your work. I hope listeners will also go take a look at your papers. You have a lot of very interesting research, and I am excited to see what you do next.
Yeah, thanks a lot, Daniel. Thanks a lot for having me, and it was really fun to chat.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.